we were looking at this example, okay, and before this example we discussed the concept of demand, volume and capacity, right? Now out of these three things, which are shown in this figure? Demand and capacity. Which one is demand? Everybody starts doing this. And which one is capacity? The horizontal line. Okay. What did we calculate from this figure? We calculated two things yesterday. Which was what?
That would be lift over the state and certain.
And these cars are where?
At the road itself.
Okay, and they are in the
intersection.
queue, right? So we calculate the length of the queue. You call it the length of the queue, number of cars in the queue. Okay, and what else? Yes. What else did we calculate? Is it not given? Rate of cars moving on. Yeah, the time for the queue to move. Okay, like it will be completely gone. That time. Okay, so that time came to be 270 minutes, and the number of cars in the queue was 2,700 meters. Okay. Now the third thing which is important for us in this condition is the delay. How much will be the total delay for everybody, and how much will be the average delay for each person? Okay. To do this, we need to do some calculations first. We will draw another figure, but to draw that figure we need some calculations. Okay. So okay, I have time, I have how many vehicles arrived and how many vehicles departed or left. Okay, so at each time interval or at each point of time, how many vehicles have come and how many vehicles have left. Clear? There is a calculation we want to do. Okay. So let me set the time. I'll start from 0, right? Then the next time is 30. Now keep these values in mind. I will ask you why did I take them. Okay. The next one is 90 and the next one is 360. You see the values now. 0, 30, 90, 360. Okay. Tell me, why did I take these values for time? 0 is fine. You always start from 0, no problem.
Yeah.
Why did I take the next value as 30? Demand is increasing. The start of what? Okay.
Demand more than capacity.
Demand more than capacity. What started from this point? Q. The Q started. Okay. Next value I took was 90. Why?
Then
The end of?
demand more than capacity.
Demand more than capacity. The end of demand more than capacity. Okay.
Start of the queue.
Start of Q.
The queue.
Start of the end, right? Huh? Very, very theoretical. Okay. Start of the end of the queue, right? Q starts to move now. Demand is less than capacity, Q starts to move. Okay, 90, fine. Why next time is 360? Huh? Which change? What will happen at time 360?
It is needed 270 minutes to for the queue to move.
Yeah. For the queue to move completely, I need 270 minutes. And these 270 minutes start from 90. So 90 plus 270 is 360. Okay? Some of you don't trust me, you can calculate, no problem. 90 plus 270 is 360. Okay? Clear? So I took the times from the changes in demand and queue and so on. Okay? So if you didn't do the earlier calculations, you don't know what times to take. If you don't have this graph and the calculation, you don't know where to calculate the vehicles arrived and departed. Okay. At time 0, how many vehicles arrived? At time 0, how many vehicles arrived? 60 by 60. Yes, 0. If nobody arrived, then nobody. No. We haven't started yet. We haven't started yet. Okay, time 0 means what? You didn't start yet. Okay, so if you didn't start, you don't have anything. Okay, at time 30, how many vehicles arrived? Now these are, keep in mind, these columns are cumulative. I will add it here. Cumulative, both of them. Okay, so I'm asking for cumulative number. So when I say time 30, I mean from 0 to 30. How many vehicles arrived? 50 only. This is 50 per minute. 50 per minute. Okay. So 0 to 30 means 30 minutes, right? And every minute 50. Total is okay. Let us fill this column first. It's easier. Okay, we'll move on to the other column next. Okay, next time is 90, right? So again, it's cumulative, so I mean 0 to 90. 0 to 90, okay? How many vehicles arrive between 0 to 90? So for the first 30 minutes, it is 50 per minute, right? And for the next 60 minutes, it is 120 per minute, okay? So 30 into 50 plus 120 into 60. For the first 90 is here. Okay, 90 is here. So in the first 30 minutes, vehicles were coming at a rate of 50 per minute. Then they came at a rate of 120 per minute. So I will add this plus this. Multiplying by time, okay? So 50 into 30 I already know, that is 1500, right? So I will just add it here. Plus 120 into 60. Okay. Any questions? There. Okay. Next. Time 360, somewhere here, out of the graph. It's not shown here. Okay. But the rate is same. You see, the line will continue. This will continue. Yes, I am sure. You asking me, I am sure. If I say no, what would you do? This has never happened. Okay. Time 360. So from 0 to 360, how many vehicles arrive? In the first 30 minutes, we know. next 60 minutes, we know, we already calculated till 90, right? So after 90, they are coming at a rate of what? 65 per minute. Okay, and how many minutes they are? From 90 to 360, 270 minutes, right? 270 minutes. Okay, so I will add whatever number I had at 90 plus 65 into 270. Two six two five zero. Any problem up till now? Clear? Sure. Sure. Okay. Now vehicles departed. Now we are talking about vehicles leaving, okay? Vehicles leaving. In the first 30 minutes, what was the rate at which the vehicles were leaving? Huh? Same, right? Because it was less than capacity. So they were leaving at the same rate. When they were coming at 50, they were leaving at 50 per minute as well, because it was less than capacity. Okay? So there was no queue, right? Up till this point, there was no queue. In the first 30 minutes, no queue, no problem. In the next 60 minutes, what was happening? Vehicles arriving at 120, but they were leaving at what? What was the rate at which they were leaving? 75, because this is what? Capacity. It cannot be more than capacity, right? So up till 30, it is 1500. After 30, it is 75 per minute. Okay? So whatever I have at 30 plus 75, how much? 6,000. Okay. Now what is happening in the next 270 minutes? At what rate they are leaving? Yes. Why 75? Why not 65? Huh? We have a queue, right? So 65 are the new, but 10 are leaving from the queue as well. So they are leaving at 75 still. Okay, until you get rid of the queue, it will remain 75. Okay, until there is a queue, you will keep on going at 75 until you clear the queue. You cannot go below 75, right? Okay, clear? Okay, so whatever I had up till now plus 75 into 270, and this is equal to what? Why they are equal? Why they are equal? Because
We need 270 minutes.
no. Why did they become equal? Because what happened? There is no queue. What other time they were equal? At 30, because there was same. There was no queue. So whenever the queue is gone, whether it's a previous queue or it has not started yet, whatever the case is, okay, the queue has not started yet at 30, so they are equal. Then the queue started, but at time 360 the queue is gone, so again they become equal. Whenever you get rid of the queue, these two columns will become equal. Okay, now using time and these two columns, they have drawn a graph. Okay, and the graph this is. The two lines which you see in the graph are for the vehicles arrived and departed. Okay, now you can see till time 30, both lines are same, right? They are going together. Okay, this is almost zero, almost, because the number is very small. It's not zero. Keep in mind. At time 30, it was not zero, right? Huh? It's not zero, right? Okay, but number is very small compared to the graph, scale of the graph, so it's looking zero. Okay, but it's not exactly at zero. It's a very, very small number. Keep in mind. But the point is the lines are same because the numbers are same, both lines 1500, 1500. Okay, so they are together and the number is very small. Then what happens from this point onwards? Both lines are separated now. Okay, so this is the line which is, you can see, is going constantly, right? So which line is this? Arrival or departure? Which thing was constant? Departure was constant, right? 75 per minute. The departure was 75 per minute, right? It didn't change. So this is the departure line. What about the arrival line? It was 120 per minute, then it became 75 per minute, right? So you can see the change here. Okay? You don't have to worry, you don't have to do it yourself. You just plot the points and join them. They will become like this by themselves. Okay, I'm just giving you some checks. When you draw it yourself, you know what is happening. Okay? Clear? Huh? Okay. Now, from this graph, I want to calculate the delay. From this graph, yes. Huh? Departure. Departure is this is departure. The other one is arrival. So it was 120, then it became 65, and this is 75 per minute. So you see the rate is shown as a slope. Okay, why the slope changed here? Because the rate changed. Okay, so the rate changed for arrival. It did not change for departure. Okay, and you can see at this point they meet again. Which point is this? 360, because the Q is gone. Clear? Okay, now how do we calculate the delay? Once you have plotted this graph, delay is difference in area under these two lines. What is delay? You calculate area under both lines and take their difference. Delay. Okay, area under this line and area under this line, and then you do what? Calculate its difference. Got it? Clear? Any problem? Okay, now look at the area under the departure line. Departure line, this one, the bottom. It looks like what? A triangle. Do we know how to calculate the area of a triangle? Sure. Now this is for everybody. Sure, right? You know how to calculate the area of a triangle. It's equal to what? Huh? Half base what? Half base into height, huh? So how much is the base? We are going from 0 to, from 30. We are going from 30 to 360. So base and height is how much? You have the number, right? We calculate this number, right? We have 26, whatever. Half base into height. Got it? Now what about departure? What do? You will make two triangles, right? So this is one triangle and this is the other triangle. Okay? One triangle. Okay? The other one is not triangle. Okay, sorry. The other one is a triangle and a rectangle. Okay? But you know how to, you have the number, you can calculate the area. Okay? But if you calculate one area and then you calculate the other area and you take the difference, they have given us a simplified equation. But you get the idea what we are trying to do. What we are trying to do, calculate area under both lines and take the difference. Okay? If you do this, this is a simplified version of what you will do in the end. Okay? So half 90 minus 30. This. Okay? This was 30, this was 90, right? So half 90 minus 30 multiplied by the difference of these two lines, which is how much? 2700. Number of vehicles in the queue, right? How many vehicles are in the queue? 2,700. Okay. Plus again half. Now how much is this portion? This is 360. This is 90. Okay. So 360 minus 90, and again the difference between the two lines, which is 2,700. Okay. How much is the answer? This is the answer. Okay. If you took area under this line and area under this line, and then you took the difference, you will get the same answer. Okay. Again, will I always get these type of lines? The shape can change, right? It can have changes at multiple points. Okay, so that's why it's important you know how to calculate it. Okay. They simplified the calculation, but in the end what they are doing, area under the arrival line and area under the departure line, take both areas, take the difference. The answer will be good. Okay, this is what now? This is total delay. This is total delay. Okay, you can see it's a very large number, 445,000 and something. Okay, it happened because of demand going over capacity for 60 minutes, right? It happened for 60 minutes. Okay, and it caused this much delay for everybody. Now when I say total delay, what do I mean? I mean delay, so you were delayed for 10 minutes, you were delayed for 5 minutes, you were delayed for, you came late, right? So you were delayed for 20 minutes. Okay, you came in later, so you were delayed by 30 minutes. Okay, so I took all these values and I add them together. So this will be total delay. Got it? Now I want to calculate average. You have total, right? How do you calculate average from total? Divide by number of vehicles. Number of vehicles who were where? In the queue. In the queue. Number of vehicles who were in the queue. Okay. Now how many vehicles are in the queue? How many vehicles are in the queue? How many vehicles in the queue? The vehicle which was in the queue, they had the delay, right? So how many vehicles are in the queue? Yes. How many vehicles? No.
All the vehicles after 30 minutes.
Sorry.
All the vehicles after 30 minutes.
All the vehicles still
After 30 minutes.
after 30 minutes. When did the queue start? At 30, right? So everybody who came after 30, they joined the queue, right? They have to. Okay? And till what time it continued?
This is
Okay? So from 30 to 360. Okay? We have the queue. So whoever came during this time, he was in the queue. He joined the queue. Okay? Now how many vehicles came during this time? From here to here, they were coming at 120 per minute, right? From 30 to 90, they were coming at 120 per minute. And from 90 to 360, they were coming at? Coming. 75 was going. They were coming at 65 per minute. Okay, so from here to here, 120 per minute. From here to here, 65 per minute. So whoever came during this time, they had to face the queue. And how many are these vehicles? These are 24,750 vehicles. between time 30 and time 360, how many beakers came? 24,750. You can see how they calculated. 60 into 120 in this portion, and then 270 into 65, which is this portion. Okay? Clear? Any question? Clear? Okay. So total number of vehicles is this. Total delay is this. I want average. I will do this upon this. Okay. And what do you get? 18 minutes per week. So on average, a driver was delayed by 18 minutes. Whoever came during this time between 30 and 360, he was delayed on average by 18 minutes. Some of them less, some of them more, but this is an average number for all of them. Clear? Clear? Sure. Any questions?
The slope of the 360 minutes, would it be equal to 65?
Sorry? Slope is 65, yes. This one. For this line? After, yes, 65. Yes. Until I change the demand, it will remain 65. Clear? Any other question? Okay. What you saw in this example is called a breakdown. Okay? Breakdown is when demand goes over capacity. Then we create a breakdown situation. Okay? So what was happening between time 30 and 90 was a breakdown situation. And you can see how much delay it caused, how long was the queue, and so on and so forth. Even the queue was more than 2,000 vehicles, right? Okay? So the breakdown can happen, normally it can happen at any location. Okay? But normally these are the three locations where breakdown usually happens. Okay? The first one is an on ramp. So there's a bridge and people are entering the bridge from a ramp. Okay? So it may happen that this additional flow from the ramp is more than the capacity of the bridge. So it will create a breakdown. Okay? Second is merge point. There is one highway, there is another highway. It's not a ramp, there are two highways. Okay? Ramp is different and a highway is different. Okay? You get this point, right? Okay? So there are two highways and they are merging into a single point now. Both of them are main highways. Okay? So the total flow from highway 1 and 2, their summation can be more than the capacity of the next segment. So it will create a breakdown. And then the third one is very obvious. If you understand the first two, is intersection. Intersection is a point from where traffic on one segment can come from three different directions, right? So the summation of all these directions can be more than the capacity. Okay, so again a breakdown can happen. So any point from where traffic can enter your segment, it can create a breakdown. And these are the three common points where it happens. Okay, we will look at examples for two of them. This one, you can see I have a segment, approach 1, approach 2. And then they come together and join on approach 3. So which case is this? Second one, the merge point. This is a merge point. Okay. For each segment, you can see the capacity, demand, and volume. C capacity, D demand, V volume. For each of them is given. Okay. For the first case, capacity of approach is 4,000. Demand is 3,800. So the volume will be 3,800, right? It's less than the capacity, no problem. Same thing here. Approach 2. Capacity is 4,000. Demand is 3,600. So volume is 3,600. Less than capacity, right? No problem. But the demand of approach 3 is written as 7,400. How did I get 7,400? Demand of this, demand of this. This segment is combination of these two, right? So demand of this and demand of this. Okay. But capacity is as per design. It's not as per demand. The capacity is what? 6,000. Okay. Now you see demand is more, capacity is less. It will create something which we called as what? Breakdown. Okay. So the actual volume will be 6,000. The same which we saw in the last example, right? If the capacity is 75, you have a breakdown, the flow will be 75, not more than that. Okay. So here the capacity is 6,000, the breakdown happened, and the volume is 6,000. So there is a lagging of some vehicles, right? These vehicles will make a queue. Where will they make the queue? At the entry point. From this point onwards, 6,000 vehicles will move. Behind this point, they will start to have a queue. So the queue area is shown as these zigzag lines. Okay? Clear? Another example. This is for the ramps. And these are multiple ramps. Okay? So there are 4 ramps. One highway, 4 ramps. Okay? Figure A gives you demand. Figure A gives you demand for segment or ramp, any one of them, either for the segment or for the ramp. For segment 1, this much. For ramp 1, this much. Now you can see the direction of the ramp, right? Is it going in or out? In. This one, in. This one, out. This one, out. So this 800 is the demand going in. 700 demand going in. 500 demand going out, and so on. Clear? Second figure gives you the capacities for each segment. Ramp, we don't have any problem. We are not considering that. Whatever the demand is, it does not affect the capacity. The capacity is good enough for the ramp. There is no problem of capacity. Okay. So the capacities are only given for the segments. You can see the value. Okay. And in this figure, we are supposed to fill in the volumes. We are supposed to fill in the volume. Some of the values are given, and some of the other values we will fill in. Okay. First segment. Look at the demand. Look at the capacity. How much will be the volume? Right? Because the demand is less than capacity, so it's the same. No problem. Okay? Second. Okay, why 3,000? 2,200 plus 800. 2,200 demand of segment 1 and 800 demand coming in. So total 3,000. Clear? Huh? Okay. Next one. What is the demand? Segment 3. I'm talking about segment 3. What is the demand? 3,000? 3,700, right? 3,000 in segment 2. So I will write it here because demand and it's not the volume. Okay? So 3,000 up till here plus 700 entering from here. Total demand is 3,700. But the capacity is 3,400. Okay? So the volume is 3,400. So now what happened? No. Like what do we call this situation? A breakdown. Okay? Breakdown happened. Okay. Now, after that, they did something which you usually see in the slides. Number is given. How did I get this number? We don't know. Okay, so remember these are volumes, right? So here it was 3,400. Okay, first of all let us look at the demand. What is the demand of segment 4? 3,700 till here, and how many going out? 500. So demand for segment 4 is 3,200. Okay, but why? And the capacity is how much? 3,000. So it should be one of these numbers, right? But they have written 2941. What is this? And I told you there is no problem of capacity on the ramp, right? So why don't I have 500 here?
All of them exit there.
500 are still optimized.
Yeah.
Not all of them exit there.
All of them what?
Not all of them exit.
Why not?
They change that.
They change the route. Very good.
The capacity is about 500.
Now, same as what she said. This is what we call the network effect. Network effect. Okay, what is a network effect? If you have a breakdown in one segment, it will proportionally affect all the other segments as well, irrespective of their actual demand or actual capacity. So this 2941 is not because of these two numbers, 3,200 and 3,000. This 2941 is because of segment 3. Segment 3 is a breakdown, right? There's a breakdown. And breakdown, some of the people are stuck. Okay? Actual was 3,700. And you have 3,400. Okay? So how many are stuck in queue? 300. So obviously some of those 300 must be going out from here, right? From the ramp. The people who are going out from the ramp, they are part of this 3,700, right? So out of this 500 or out of this 3,700, 300 are still stuck. So this one cannot be 500, right? 500 now. It would have been 500 if you allow 3,700 from segment 3. But we are not allowing it. So some of this 500 will reduce. How much? It has a proportional effect. What do I mean? You have to see what proportion of the actual demand you are allowing in segment 3. And the remaining segments will reduce by the same proportion. Okay? So for example, what proportion you are allowing in segment 3? The actual was 3,700, right? And you are allowing 3,400. So what proportion is this? Proportion. Sorry. Sorry, I did the other way around. Do this, 1 upon this. So you are allowing 3,400 and the actual is 3,700. You are allowing 0.92. So that next ramp will have 0.92 of its demand, irrespective of the capacity, irrespective of the volume. This is a network effect. Okay? So instead of 500, I will have 0.92 of 500. How much is 0.92 of 500? 4.5. Okay? Not okay? The actual demand, Why are you doing this?
No question.
Okay. Okay? So 459 is what? 92% of 500. Why 92%? Because from segment 3 onwards, I am allowing 92% of actual demand. Clear? Sure. Any question? Because I want to calculate what percentage of actual demand I am allowing forward from segment 3 after breakdown, yes. Okay? So how did I get 2941? 3,400 minus the one which I am allowing forward. So 2941 is this one. Okay, and the same thing here. The actual was 400, but it will not be 400, it will be 0.92 of 400, which is how much? 368. So 2941 minus 368. Yes. Clear? Any questions? Any questions? Okay. So first thing is, you see the network effect. If there is a breakdown in one segment, the next segment will see the effect of the breakdown, irrespective of their actual volume, their actual demand and their actual capacity. Irrespective of that, they will see the effect of the breakdown in the previous segment. Okay. The segment which has the breakdown, we call it the bottleneck. So segment 3 is what? It's a bottleneck. Okay, what is the bottleneck? The segment which has what? A breakdown. Okay, a segment which has the breakdown. Why do we call it the bottleneck? You see the shape of the bottle. This is the neck. Neck is small. Okay, that's why we call it the breakdown. This is a smaller segment which is creating the flow in the next one, or affecting the flow in the next one. Got it? Okay. Yeah. Now somebody asks you, I have a problem on this highway. You analyze this data and you say segment 3 is a problem, right? Segment 3 is a bottleneck. We must do something about segment 3. Okay, so somebody comes and says, okay, let us increase the number of lanes. It will make segment 3 bigger, so it will have the demand now. Okay, so you make segment 3 bigger and the demand goes to, demand was how much? 3,700. So the volume will be 3,700. Okay, now what will happen on the next segment? What is the demand of next segment? 3,200. What is the capacity? 3,000. Now what will happen in segment 4? A breakdown. And now what we will call segment 4? Bottleneck. Okay. If there was no breakdown, forget about segment 3. Let's say you are starting from segment 4. Look at the demand, look at the capacity. It is a bottleneck, right? Demand is more than capacity. It is a bottleneck. Okay. But with segment 3, in the current condition, in this condition, it is hidden. It is what? Hidden. In this condition, the actual flow in segment 4 was only 2,900. So there was no breakdown here. Okay, but if you look at the actual flow and actual demand and actual capacity, it should have been a breakdown. Okay, so this is what we call as a hidden bottleneck. A hidden bottleneck. What is a hidden bottleneck? It has demand more than capacity, but the previous segment is blocking this demand. So there is no breakdown there. Okay, so in segment 4, demand was more than capacity, but segment 3 is blocking the demand. So that's why it is hidden. Okay, bottleneck is what? Demand more than capacity, right? It is in segment 4 as well. But why it is hidden? Because of segment 3. Clear? Okay. Now something which we have seen in all the examples we have done up till now, even in half of this example, even the previous one. This is equal to what? 2,200 equal to demand. 3,000 equal to what? Demand. 3,400 equal to what? Capacity. If you go back to all the previous examples in which we did this, the volume is either equal to demand or capacity. But what happened in segment 4 and in these ramps? 2941, is it equal to demand? No. Is it equal to capacity? Okay, so this situation is called as demand starvation. This is called as demand starvation. What is demand starvation? When volume is below demand and below capacity, both. Okay, in normal conditions, volume is either equal to demand or equal to capacity, like what was happening up till segment 3 here. But in segment 4, you got 2941. Capacity was 3000 and the demand was 3200. So volume is not equal to demand and not even equal to capacity as well. It is less than both of them. So we call this as demand starvation. When volume goes below demand and capacity, we call it demand starvation. Clear or not? Why demand starvation happens? The effect of a bottleneck. But where is the bottleneck? Before. Okay. The term which they use for before in traffic is upstream. We have traffic stream, right? So when it is before, we call it upstream. When it is after, we call it downstream. Okay. So demand starvation happens because of an upstream bottleneck. Okay. Clear? Any questions? Yes. Before. Okay, anything, so you are considering this segment, anything which is before, we call it upstream. Anything which is after, we call it downstream. Okay. Any questions? How to? Sorry? How what? What else?
I'm just asking that we should just only know, one must calculate, we must.
You calculate it, right?
Okay.
This can happen. Demand capacities can be given, and I may ask you, okay, give me the volumes.
But after the efforts of
We calculated here, right? I told you how they calculated these numbers. This is, you calculate the proportion, and then for each RAM you will apply the proportion. So I know this is 0.92 of 500. I know this is 0.92 of 400. Okay, and 34,400 minus 459. Okay. Clear? Any other question?
The second, when the observed volume is 700.
Which one?
Second one.
Yeah, 700. Yeah. Ramp has no problem of capacity in this problem. So in this case, ramp has no problem of capacity, so it will be 700. But if I tell you the ramp has a flow of 1000, capacity of 800, then yes, this ramp will become the bottleneck. And there will be a breakdown on this ramp, not on the highway, on the ramp. Okay? Clear? Any other question? Okay, now a word of caution. You can see the examples which we have done in this chapter, especially in traffic flow theory onwards, up till now. When we started traffic flow theory up till now, all the examples are case-to-case basis. We use some graphs, we derived our own equations. Here, even here, do all highway have 4 ramps? Is it necessary that highway must have 2 on ramps and 2 off ramps? No. Okay, so when things change, the numbers will change, your calculations will change. But you must have the concept, what is demand, what is capacity. Okay, when the demand goes over capacity, what will happen in the next segment and the next segment after that? How do I calculate delay? How do I calculate Q, and so on and so forth? Okay, I already mentioned some books, they are uploaded, they are solved examples, you see them, okay, you can solve them, and so on. You guys also have a way of getting the old exam papers, right? So look at them. Okay.